If you take a close look at the periodic table of chemical elements, you'll see that the most affordable metals are mostly located at the top, since they are the most abundant on our planet primarily because of their low atomic mass. Of course, there are some minor exceptions like lithium, beryllium, and boron, but the overall trend remains the same. The lighter the element, the more abundant it is on Earth, and accordingly the cheaper it is. A similar trend is observed in the universe. There are a great many light elements in the universe, so many in fact that the lightest ones, namely hydrogen and helium, make up 98% of all atoms in the universe, while only 2% of all other atoms are made up of heavier and more expensive elements. Metals, by the way, make up only 0.2% in space, and even then, 90% of those are light metals like aluminum or magnesium. The rarest metals in the universe, just as on Earth, are the platinum group metals, especially rhodium and rhenium. This is all due to a rare nucleosynthesis process in which the probability of forming these elements is extremely low. But still, we mine minerals only from the thin solidified crust of our planet, which is where humanity gets all possible chemical elements. With our current level of technology, mining any deeper is not yet possible. Well, unless we drill some kind of super tunnel like in the movie The Core. Therefore, if we look at the abundance of elements in the Earth's crust, we can already see some small differences compared to, for example, their abundance in space. For instance, there is very little hydrogen and helium on Earth, while boron and beryllium are present in about the same amounts as zinc. Otherwise, the trend is somewhat similar to the cosmic abundance of elements. There are many light metals in the Earth's crust, but far fewer heavy ones. But unlike their cosmic abundance, gold and platinum group metals are, on average, 150 times less abundant in the Earth's crust than they should be. This is all because these elements react with very little, and during the early stages of our planet's formation, they existed in the protoplanetary cloud in a free state. Because of this, most of them fused with iron and nickel, which were simply abundant in space. And after our planet formed, they all sank together into the iron core and disappeared underground. This process was made more straightforward by the fact that valuable precious metals have a tendency to dissolve quite easily in molten iron, even when considering that the melting points of some of these metals can be considerably higher than that of the iron itself. That is exactly the reason why, in one of my previous videos where I made an alloy from almost all metals, I used iron as the base, since many metals, especially platinum or rhenium, dissolve quite easily in it, behaving much like sugar in water. As a result, because of this affinity of precious metals to alloy with iron, most rare metals are now located in the center of our planet, and there's simply no way for us to extract them. But if you think about it, if all the precious metals had originally alloyed with the iron core, then the Earth's crust would have become almost sterile, and we simply wouldn't find any rare metals in it. But it's not that simple. While gold and other precious metals still remained within the solid rock in trace amounts, most of these valuable elements were brought to our world by intense meteorite bombardments, of which there were a vast number over the 4 billion years of our planet's long history. And since the concentration of gold and platinum group metals in meteorites is quite elevated, these precious elements gradually became integrated with the metals that were already found within the Earth's crust. Gold, being the most inert metal, is mainly found in its pure form, while the other precious metals are obtained as byproducts, for example from copper-nickel ores, since they have chemical properties similar to nickel. If we look at prices, the most expensive of the platinum group metals right now is rhodium, which costs about 350 euros per gram. So what about even heavier metals? After all, in theory, there should be even less of them, and they should be more expensive. There's a small paradox here. If you look at the table of element abundance in the Earth's crust, and try to find the heaviest elements, namely the radioactive uranium and thorium, it turns out that there are several times more of them in the Earth than there are precious metals. And in terms of dispersion, they're similar to tin. But how is that possible? If we look at thorium separately, it is actually the most abundant radioactive metal on Earth. And that's not surprising, since its half-life is as much as 14 billion years, which is comparable to the age of our universe. Thorium in the universe is formed during the merger of neutron stars, when atoms of other elements are bombarded with neutrons like from a machine gun. Because of this, uranium and thorium are produced more quickly than, for example, rhodium or gold. And since it has an incredibly long half-life, thorium in space can exist indefinitely for an almost infinite amount of